Dear students, let us start the class. I am discussing about differential equations, which is coming under the paper Mathematical Physics and Error Analysis. So let us begin our discussion. Many physical laws and relations can be expressed mathematically in the form of differential equations. Basically, there are two types of differential equations. First one is called ordinary differential equation and second one is called partial differential equations. The word itself says ordinary differential equation contains ordinary differentials, and at the same time partial differential equations contains partial differentials. So these are the two types of differential equations. Ordinary differential equation represented as ODE and partial differential equations represented as PDE. Understanding the basics of ODE requires solving problems by hand. So, dear students, please listen to the class with paper and pen. In doing so, you will gain an important conceptual understanding and feel for the basic terms such as ODEs, its solution, direction field, and initial value problems, etc. Now we are discussing modeling. If we want to solve an engineering problem, usually of a physical nature, we first have to formulate the problem as a mathematical expression in terms of variables, functions, and equations. Such an expression is known as a mathematical model of the given problem. The process of setting up a model, solving it mathematically, and interpreting the result in physical or other terms is called mathematical modeling, or briefly modeling. And the various steps of modeling is shown in the next slide. Here you can see four blocks. First block says physical system, next is mathematical model, next is mathematical solution, and last one is physical interpretation. So in the process of modeling, what we are doing is we will first identify the physical system and we will construct a mathematical model for that particular physical system. Then we will solve the mathematical model by using some appropriate mathematical methods. And last, we will interpret the solution and we will suit the solution. And we can see that the solution suits very well with our physical system. So these are the steps involved in the process of modeling. Then applications of differential equations. You can see three figures, and in the first figure you can see falling star, and here the differential equation is y double dash is equal to g, which is equal to a constant. Y double dash means d square y by dt square. And in the second case you can see a parachutist going downwards, and here the differential equation is mv dash is equal to mg minus bv square. M is the mass, v is the velocity, g is the acceleration due to gravity, and b is some constant. And here the equation is given. And in the last case, water level h, outflowing water, h dash is equal to minus k into root of h. And all these examples we will discuss in detail in the due sections. So differential equations have many practical applications. Now we can define an ordinary differential equation. It is an equation that contains one or several derivatives of an unknown function, which we usually call y of x or sometimes y of t if the independent variable is time t. The equation may also contain y itself, non-functions of x or t, and constants. Let us see some examples. Y dash is equal to cos x. The order is 1 because we have y dash only, dy by dx. And in the second equation the order is 2 because we have d square y by dx square. And in the last equation we have two differentials. One is dy by dx and another is d cube y divided by dx cube. So here the order of the highest derivative is 3. So naturally the order of the differential equation is 3. So this is about the order. How can we define, how can we identify the order of the differential equation? Just check what is the order of the highest derivative involved in the differential equation. The order of that highest derivative gives the order of the differential equation. Now, here we will be considering only about first order ordinary differential equations. Such equations contain only the first derivative y dash and may contain y and any given functions of x. Hence, we can write them as f of x, y dash is equal to 0, or in another form as y dash is equal to f of x, y. This is called the explicit form. That means y dash is equal to f of x, y is called the explicit form, and f of x, y dash is equal to 0 is called the implicit form. So there are two forms of a differential equations. First one is called explicit form and second one is called implicit form. Now, what do you mean by the solution? A function y is equal to h of x is called a solution of a given ODE on some open intervals a less than x less than b if h of x is defined and differentiable throughout the interval and is such that the equation becomes an identity if y and y dash are replaced with h and h dash. The curve of the h of h is called the solution curve. As an example, you can consider the case of x y dash is equal to minus y, which is the differential equation, and we are checking whether y is equal to c by x is a solution. So what we are doing is, you insert the value of y in the given differential equation and check whether the equation is correct or not. And if the equation is correct, then we can say that y is a solution of that particular differential equation. So here in this problem, you can see that y is a solution of the given differential equation. Please see the problem. Now, another type, solution curves. Here we are considering another differential equation, y dash is equal to cos x. You just integrate and we will get the solution as y is equal to sin x plus c. Here c is called an arbitrary constant. So you will be getting a large number of curves corresponding to different values of c. So in the solution, figure 3 shows many curves corresponding to different values of c. So all these curves are the solutions of the given differential equation y dash is equal to cos x. So in this way also you can say what you mean by the solution of a differential equation. Here also you can see two types of figures. First one is called exponential growth, figure 4a, and figure 4b shows exponential decay. So if y dash is equal to some 0.2 e raised to 0.2 t, then the solution gives exponential growth. At the same time, if the power of the exponential is changed to minus 0.2 t, then you will be getting solution as exponential decay. So these types of solutions are also available, exponential growth and exponential decay. Now we can see that each of the above solution of differential equations, there is an arbitrary constant c. Such a solution containing an arbitrary constant is called general solution of the ordinary differential equation. Geometrically, the general solution of an ordinary differential equation is a family of infinitely many solution curves, one for each value of the constant c. In the previous slide, you can see a large number of such curves. All such curves are said to be general solutions of the given differential equation. If we choose a specific value for c, we obtain what is called a particular solution for the differential equation. A particular solution does not contain any arbitrary constant. So there are two types of solution for a differential equation. First one is called general solution consisting of arbitrary constant c, and another one is called particular solution that does not contain arbitrary constant c. Next, we are discussing about initial value problem. In most of the cases, The particular solution, or it is called the unique solution of a given problem, is obtained from a general solution by imposing an initial condition. Here we can consider an initial condition as y of x0 is equal to y0 with given values of x0 and y0 that can be used to find the value of the arbitrary constant. So, if you are imposing an initial condition to a differential equation, the solution obtained is called a particular solution. So that is what initial value problem means. So geometrically, this condition means if you are imposing an initial condition for the differential equation, it means that the solution curve should pass through the point x0 and y0 in the xy plane. An ordinary differential equation together with an initial condition is called an initial value problem. So an initial value problem will be always consisting of an initial condition, and the solution will be a particular solution only. There is no general solution for initial value problems, only particular solutions are available. So thus, if the ODE is explicit, y dash is equal to f of xy, the initial value problem is of y dash is equal to f of xy, y of x0 is equal to y0. And here you can see an example for initial value problem. And here y dash is equal to 3y and y of 0 is equal to 5.7. So this y of 0 is equal to 5.7 can be used to find out the arbitrary constant, and thus you will be getting only a particular solution of this given differential equation. And another example is radioactive decay, radioactivity. And here this can be considered as a problem, and this can be also considered as an example for modeling process. Okay. So given an amount of radioactive substance, say 0.5 gram, find the amount present at any later time t. So this is our problem. We have a radioactive substance of having some mass, and we have to find its mass after some time. And the physical information is experiments show that at each instant of a radioactive substance decomposes and is thus decaying in time proportional to the amount of substance present. Here there are 3 steps for modeling or solving this problem. Step 1, setting up a mathematical model of the physical process. Step 2, mathematical solution for the physical process. Step 3, interpretation of the results. So the whole process consisting of modeling radioactivity, exponential decay. Okay, so if you read the given information, given note, you can understand very well how radioactivity happens and how differential equation is used to interpret the results. And in the next slide, I added a video to explain very well the radioactive decay. Please listen the video carefully.
So we've seen that the differential equation dy on dx equals kx gives rise to the equation that describes exponential growth. So y equals a by e to the positive kx describes exponential growth. Well, what if we were to turn the coefficient in front of this y here on the right hand side, this k, into a negative, so we have negative k instead of positive k. So if we work through the solution and separate the variables, dy on y equals negative k by dx. So in case you haven't seen the previous videos, we simply move all the y's to the left hand side and move all the x's to the right hand side, and then we integrate both sides. Working these integrals through will eventually come to the solution y equals a by e to the negative kx. So this is an equation here that describes exponential decay. So we have e to the positive kx modeling exponential growth and e to the negative kx modeling exponential decay. Alright, so what does this mean physically? Well, this is what the family of solutions y equals a by e to the negative kx looks like for several values of k. Actually, in all of these examples, we have a equals 3, the coefficient in the front. So the equation is 3 by e to the negative kx. This olive curve here is when k equals 1/4. The magenta curve is when k equals 1/2. This cyan curve here is when k equals 1. The orange curve, k equals 2. And the blue curve is for k equals 4. So k describes the rate of decay. So it's the decay constant. And as we can see, the larger the decay constant, the quicker the rate of decay. So physically, these might represent something like radioactive decay. And we can use the equation to see if radiation levels are safe from the time of, for example, a nuclear accident to be able to enter an area without being harmed. They might represent the charge remaining in a capacitor or a battery as it's being discharged, or perhaps the temperature of an object as it's being cooled by, say for example, forced convection. So there are many physical processes that can be described by exponential decay. Let's do an example then. Let's do an example of radioactive decay. Alright, now half-life is commonly used to describe the rate of radioactive decay. And what it simply means is how long it takes for the radioactive element to decay to half of its original amount. Okay, so let's set up this differential equation. Let's let m, big M, equal the mass of the radioactive element at time t. So m will be a function of t. So the differential equation will simply be dm on dt equals negative k times m. So this is the differential equation we'll solve to model this phenomenon, I should say, of exponential decay. And if we work through as always, we should get the general solution of m of t equals a by e to the negative kt. Now a is always equal to the initial amount, or the amount that we start off with, which is 12 milligrams. For now I'm going to leave it in symbol form. Let's let m0, so m initial, equal a, which will numerically equal 12 milligrams. So I'll rewrite the equation as m of t equals m sub 0 e to the negative kt. To work out the decay constant k, we simply consider the half-life that we're given, which is 4 hours. So what this means is then when t equals 4, at 4 hours, the mass that's remaining is equal to a half of m0. Okay, so the mass of the radioactive element remaining at 4 hours equals a half of m0. And that's of course equal to m0 times e to the negative k by 4. So if we just consider this then, we've got an m0 on the left and an m0 on the right, and these will cancel. So that implies a half equals e to the negative 4k. Take the log of both sides. Natural log and the e cancel out. So we have negative 4k equals log of a half. Now the natural log of a half, if we simply follow our logarithmic laws, is negative the natural log of 2. So we have a negative on the left and a negative on the right, and these cancel, giving us k then is equal to log of 2 divided by 4. And you'll find then this is generally how we work out k given a half-life. K is simply equal to the natural log of 2 divided by lambda, where lambda equals half-life. Okay, so the log of 2 over 4 is about 0.173. So putting that back into our solution, we've got m of t equals m0 by e to the negative 0.173 t, where t is in hours. Now we said m0 was equal to 12 milligrams. So really our function is m of t equals 12 by e to the negative 0.173 by t. So we're asked then the amount that's remaining at 4 p.m. So we started with 12 at 10 a.m. So from 10 a.m. till 4 p.m. Well, that's equal to 6 hours. So what's the mass remaining at 6 hours? So we've got m of 6 equals 12 by e to the negative 0.173 by 6, and that's equal to about 4.24 milligrams. Okay, so that's a quick example on exponential decay. I will do one more in the next video. If you have found this video to be helpful, please give me a like, and please subscribe for more videos that may help you with your studies. If you have a question, please feel free to ask in the comments below, and I'd appreciate any small tip you can give. So remember, helping me helps you, so how to do that will be in the description below. But until next time, best of luck with your studies, and thanks for watching.
So in the previous video, we have seen how the differential equations are useful to predict the radioactive decay. So as an example, we are considering how the variation of spread of corona happens in Kerala. We have a simple model. So this model is based on real data, current data. So on March 1st, the number of affected people I equal to 3. And on 23rd March, the number of affected people I equal to 95. So you can define a differential equation for this process. di by dt proportional to I, or that implies di by dt is equal to a constant k into I. So this is a very simple differential equation, and we know that the solution is exponential growth, and the solution is given as I equal to c e raised to minus kt. So by imposing the initial condition, we have obtained a particular solution for this differential equation, and that is equal to I equal to 3 e raised to a constant into t. Okay, so based on this equation, we can predict how many number of affected peoples will be there after 30 days. And the analysis shows after 30 days, the number of people affected is equal to 8,611 numbers. But we all know that Kerala model is very famous and it is appreciated by the whole world. So we are slowly recovering from the spread of coronavirus, and thanks to Kerala government, and we must always follow the rules and suggestions proposed by the government of Kerala. Let us break the chain and stay at home, be safe. So this is taken from a textbook. The reference for this particular problem is a textbook called Differential Equations with Applications and Historical Notes by George F. Simmons, and this note is prepared by a good physics teacher, and I have used his notes to explain how the differential equation can be used to study the variation of spread of COVID-19. So this is about this lecture, and we have in the syllabus we have to discuss about basic concepts and modeling, geometrical meaning of y dash is equal to f of xy, separable ODEs and its modeling, exact ODEs, homogeneous linear differential equations, homogeneous linear differential equations with the constant coefficients, modeling of free oscillations of mass spring system. So in this lecture, I discussed section 1.1 only. So in the coming lectures, we will discuss the rest of the sections one by one. Thank you very much. And the reference are given below. Advanced Engineering Mathematics 10th edition by Erwin Kreyszig. And you can also follow the given YouTube link to understand a very famous interpretation of COVID-19 modeling by using differential equation. Please follow the link so that you can see the video from YouTube. Please feel free to ask questions and doubts. My address is given, my phone number is given, and my name is Vinod Kumar, and I am an assistant professor of physics at Department of Physics, Pioneer College. Thank you very much. Be safe, stay home, and let us break the chain. Thank you very much.